Good morning. Now we are going to see the temperature dependence on a rate of a chemical reaction. Generally, as the temperature increases, the rate also increases. For example, in case of nitrogen pentoxide N2O5, the decomposition of N2O5 at 50 degrees Celsius, the decomposition of N2O5, the 1 mole of N2O5 can decompose by 12 minutes. But at 25 degrees Celsius, as the temperature decreases, the decomposition need 5 hours to complete. And at 0 degrees Celsius, with low temperature, it takes 5 days. That is, as the temperature increases, the rate of chemical reactions also increases. And in your lab, permanganometry titration, you have to warm the oxalic acid to 60 degrees Celsius to titrate against the permanganate solution to increase the rate of decolorization of permanganate. Okay, that is, as the temperature increases, the rate also increases. The dependence of temperature on rate is first proposed by Van Hoff, but give a mathematical equation, a correct mathematical equation by Arrhenius. And by Arrhenius, the rate constant K can be written as A e raised to minus EA by RT. By Arrhenius, the rate constant K is equal to A e raised to minus EA by RT, where A is called the pre-exponential factor and is constant for a particular reaction, and EA is the activation energy. This is the Arrhenius factor, or it is also called pre-exponential factor and is constant for a particular reaction. EA is the activation energy and R is the gas constant at a given temperature. And this is the temperature dependence of reaction on its rate. Okay. To understand the term activation energy, we can take an example of the reaction of hydrogen with iodine to form hydrogen iodide. Here, first, this in a reaction mixture, in a reaction vessel, if hydrogen and iodine are taken, the hydrogen and iodine collide with each other and first form a transition state as a very unstable transition state as hydrogen and iodine partially bond, and also the hydrogen and iodine also partially bond like this. And as soon as the transition state formed, this is decomposed to form the 2HA. That is, this bond break and the bond between hydrogen and iodine strengthened and forms the HA. The total energy, if a graph is plotted, energy against potential energy against the reaction coordinates. Reaction coordinate is the profile. Reaction coordinate means the profile of the energy change when the reactants becomes products. And here let the potential energy of reactants be these reactants. The total potential energy of reactants, let it be here. And for the formation of activation, that is the transition state, some energy is needed. That is the energy of transition state. This is let the energy level of transition state, and let the energy level of product is this. By reaction, this much energy, that is the difference in the energy. If the reactant's total energy is higher than the product's energy, that much energy is released out. But for a reaction to take place, some amount of energy is needed, that is this much energy. This much energy is needed and that energy is called the activation energy. The energy need to form the transition state, that is the unstable transition state by the collision of the reactant molecules is called the activation energy. This activation energy is different for different reactions, different molecules, and the activation, by acquiring the activation energy, then only the reactants combine to forms the transition state and forms the product. The product energy, even though if it is lower than reactants, for a reaction there needs a activation energy. Here the reactants have some amount of energy, and by acquiring the activation energy they forms an activated complex. The transition state, we can say it is a activated complex. After forming the activated complex, within fraction of a second they forms the product, and this amount of energy, the delta H, that difference in the energy of reactants, the total energy of reactants and the products, will be the enthalpy of the reaction, the enthalpy change of the reaction. Thus, the reaction, whether it is an exothermic or endothermic, is determined by the nature of reactants and the products. Okay. And now we cannot predict the kinetic energy of a particular molecule in a reaction vessel. A reacting mixture or a particular molecule kinetic energy predict cheyan kazhiyilla. And therefore the Boltzmann and Maxwell, the scientists Boltzmann and Maxwell, described the kinetic energy distribution in a reaction mixture in statistics, using statistics, and by them they plot the fraction of number of molecules turns to the kinetic energy. Let the fraction of number of molecules can be written as Ne by Nt. The fraction of number of molecules means that is Ne by Nt, means Nt is the total number of molecules and E is the number of molecules with a particular energy. Out of total energy, the number of molecules with a particular energy is the fraction of number of molecules, and it will be the Ne by Nt. And the kinetic energy, if we plotted a graph, the graph will be like this. And this, the peak of this graph represents the most probable kinetic energy. That means it is the kinetic energy acquired by most molecules. That is, let this represents the activation energy. Then this much molecules get collide to forms the activated complex and forms the product. The fraction of number of molecules under this area, representing this area, will collide with each other to forms the activated complex and forms the product. But if you give some heat energy to the reaction vessel, let the temperature now is T, and after increasing the temperature, that is giving some energy from outside, that is if the temperature becomes T plus 10, then the number of particles have more than, that is T plus 10. The number of particles with the higher energy level will increase. That is, the graph will broadens. And at this is the activation energy level, and here now the number of particles with this much activation energy increases. That is, by 10 degrees Celsius increases, the number of particles with the activation energy increases. Here, the most probable kinetic energy shifted to the right side as the temperature increases, and the fraction of number of molecules with the activation energy increases. The number of particles with the activation energy increases. Okay, this is the Boltzmann-Maxwell distribution of kinetic energy. From this distribution curve, we can understand the effect of temperature over the reaction rate. Okay. To know about the distribution curve, the Boltzmann-Maxwell distribution curve, we can take a familiar example. Let us list out the weight of 30 students, and from this list we can find out the weight of fraction of students, that is the number of students per the total number of students of a particular weight. For example, in this case 38 kilogram of weight is for 3 students in this list, and therefore the fraction of number of students have 38 kilogram is 3 by 30, that is 0.1. Like this we can calculate other number of fraction of students for each weight, and by plotting a graph between these values, that is weight and fraction of students, we get this type of graph, and the peak of the graph represents the most probable weight of the student, that is most students have this much weight in our list. Now if by the corona period the weight will increase, that is in case of so many students they becomes more fat than they had, and by using this new list we can make a data of fraction of students against the corresponding weight, and by plotting a graph with these parameters we get another graph. Here the most probable weight shifted to right side and becomes 50 here. This is the first graph we get before the corona period, and if you put the second graph over the first one we got like this, and the area in between this first and second is the number of students, number of fraction of students increase their weight by this COVID period. Okay, like this we can distribute the kinetic energy of molecules against the number of fraction of molecules in a reaction vessel. Now come back to the Arrhenius equation. That is, by Arrhenius the equilibrium rate constant K is equal to A e to the power of minus EA by RT. And this EA by RT, this e raised to minus EA by RT indicates the number of molecules which have kinetic energy greater than the activation energy. Activation energy ekal koodal kinetic energy ulla number of particles ne സൂചിപ്പിക്കുന്ന എണ്ണമാണ് the e raised to minus EA by RT. And when you take the logarithm, the natural log of K can be written as minus EA by RT plus ln A, natural log of A. That is, the logarithm form of the Arrhenius equation is ln K is equal to, natural log of K is equal to minus EA by RT plus natural log of A. And if you plot a graph with the natural log of K against 1 by T, it will be a straight line with negative slope, and the slope value will equal to, the slope is equal to minus EA by RT, and the y-intercept value. The y-intercept value will give the natural log of A. That is, by plotting this graph, we can calculate the value of activation energy and also the value of A. Okay, and let at a temperature T1, the equation can be written as natural log of K1 is equal to minus EA by R T1 plus natural log of A is constant. And at a temperature T2, another temperature T2, the equation can be written as natural log of K2 is equal to minus EA by R T2 plus natural log of A. Okay, let it this equation is 1 and this equation is 2. If you subtract the equation number 1 from equation number 2, we have natural log of K2 minus natural log of K1 is equal to minus EA by R into 1 by T2 minus 1 by T1 to EA by R into 1 by T1 minus 1 by T2. That is minus of sign angotekku poyale is equal to EA by R into 1 by T1 minus 1 by T2. Or it can be written as, or natural log of K2 minus natural log of K1 can be written as natural log of K2 by K1 is equal to EA by R into 1 by T1 minus 1 by T2 can be written as T1 T2, that is T2 minus T1. By taking the LCM, T1 into T2 is the LCM and T2 minus T1. Okay, and by changing into logarithm to the base 10, we have log of K2 by K1 is equal to EA by 2.303 R into T2 minus T1 divided by T1 T2. These are the different forms of Arrhenius equation, and this equation, that is this last one, that is the form of logarithm to the base 10, can be used for the calculate the problems based on the Arrhenius equation and to measure the rate constant at different temperatures, or you can calculate the activation energy also. Okay.